Hello, my name is Thomas Johnson, and I'm the president of the University of Saskatchewan Space Design Team. The University of Saskatchewan Space Design Team, or the USST, is made up of business students, physics students, computer science, biology, as well as engineering students from all different disciplines such as mechanical and computer. The student group was originally created in 2005 when we first started with space elevators. From then, the team moved on to nanosatellites and now works on the Mars rover for the University Rover Challenge. The team participates in these competitions to achieve its goals. The goals of the team include providing design, management, and sponsorship experience for its young and ambitious students. The second goal is to foster interdisciplinary collaboration. The third goal of the team is to demonstrate on an international level just what Canadian engineering groups can do. The focus of this video is going to be on the organization and management of the team, the design of the rover, as well as the features of the rover and how they relate to the URC 2015's competition tasks. So the USST's management is broken into a three-tier system. We have the executive committee, the team leads, as well as the general members. The executive committee is comprised of me, the president, the vice president of engineering, Austin, vice president of operations, Dan, the secretary, Chit Banu, as well as the treasurer, his name is Galen. Each position has its own sort of duties. The president's duty is basically to make sure that all the other executives are basically doing what they need to do, as well as the team leads. I have to kind of be able to know everything going on all at once. I'm kind of the go-to person for everybody, administratively as well as on the design. We have the vice president of operations, who's basically my administrative assistant, who helps me in all of my administrative tasks such as sponsorship. The secretary, besides taking meeting minutes, is also in charge of making sure our website is up to date as well as our Facebook account.
Hi, I'm Austin Shirley. I'm the VP Engineering for the team. My job primarily is to oversee the design and coordinate between the administration, between the members, and between the electrical and mechanical teams.
Hi, I'm Galen Laurent, and I was this year's treasurer for the USST. So yeah, some of my responsibilities as treasurer were to keep track of the finances. That includes all of our purchases, as well as our incoming sponsorships and donations.
So then underneath the executive committee, we have the team leads. The team leads are broken up into two. There's the electrical team lead for the electrical side of things and the mechanical team lead for the mechanical design of the rover.
At the beginning of the year, we had many design meetings in order to figure out what the goals of the rover were, and then split it into many smaller tasks so we could take advantage of our rapid prototyping tools like 3D printing.
Hi, I'm Kyle. I'm the mechanical team lead for the USST. There are many important mechanical systems on this year's rover. One of these is the rocker bogie suspension system with a differential. The rocker bogie suspension system is used to keep all 6 wheels of the rover on the ground at all times. This is very useful because it increases the traction of the rover, which is needed to climb up the steep hills and over the rocks during the terrain traversing task. Another component on the rover are the in-wheel motors. This year we placed the electric DC motors directly inside the hub of each wheel. This helps protect each motor, and it also increases the stiffness of the overall suspension system. The motors are also more powerful than the ones we had last year, allowing us to climb over rocks and up hills more easily. Another component on the rover is the mechanical arm. It has 5 degrees of freedom. It is very dexterous, which allows us to easily pick up objects off the ground and store it on the rover. The base and the end effector can both rotate continuously, which allows us to move freely without the risk of pulling out wires. The entire arm is made out of aluminum tubing, and the end effector is made out of 3D printed plastic. This makes it very lightweight. The last major mechanical part is the chassis, which all the other mechanical components mount to. This year, we made the chassis out of carbon fiber instead of aluminum. This made it 38% lighter than last year. We also made sheet metal components that completely enclose the chassis. This helps protect all the sensitive electronics from dust.
Since we wanted the rover to be lightweight this year, one of the biggest things we could do to save mass is to remove a battery entirely. But that means we had to be a lot more efficient with our power usage, and at the same time we wanted to clean up our wiring to make it more serviceable for the future. In order to achieve that, we built custom circuit boards. We were able to put more power efficient parts, custom built power supplies, and custom built motor controllers to get the most out of a single battery. The custom circuit boards allowed us to go through a lot of different design revisions, and because we built them in-house, we were able to test them and build them the same day. There's a really limited time for us to design and build and test the Rover, and so we focused on making the controls for the Rover as simplified as possible and familiar as possible by emulating video game controls. We made use of the Xbox controller in order to make the controls as familiar as possible. For example, moving your stick in a simple direction makes the Rover turn, and we used reverse kinematics in the ARM software in order to map really complex ARM movements into a simple up, down, left, right, in and out movement.
Since this competition is all about teleoperation of the Rover, it's important to have a strong software design to back up the electrical and mechanical components. Our control application is a distributed multi-threaded Python program, which is split between the Rover application and the base station application, where the Rover application is in charge of closed-loop control and sensor input, and the base application is in charge of telemetry display, navigation, and user input. We're using Arduino-style microcontrollers for the low-level control tasks, such as the reverse kinematics operating the ARM, whereas the Raspberry Pi Linux computers are used for higher-level tasks such as communication and control. Last year, our team struggled with situational awareness while driving the Rover. So this year, we made it a priority to ensure they have the tools they need to be aware of their environment at all times. This year, we'll be debuting a new vision system incorporating head-mounted display and head tracking. This will allow the Rover operator to operate the cameras on the Rover in a natural way and provide depth perception, which is useful for navigation and using the ARM.
So another part of the electrical system of the Rover is the system for the experiment, which includes a set of near-infrared lasers, as well as a photodiode used to analyze the soil. The certain wavelengths chosen for the lasers are in the near-infrared spectrum, and they correspond to certain energies absorbed by molecules, such as water and different organics. So from the amount of light reflected from the soil sample and picked up by our photodiode, we should be able to tell, with a bit of data processing, how much moisture or organic content is in the soil.
For the astronaut assistance task, our design focused on two main things: navigation and camera use. Our navigation software has evolved a lot since last year and involves topographic maps with waypoint plotting and route calculation. Our camera system involves many gimbaled cameras which allow us to scan the terrain and look for targets like astronauts or tools, as well as a 3D camera which will allow us to get depth perception to gauge distance to targets and natural head movement through head tracking.
So the main goal of the sample return task is to collect a sample of soil and analyze it in order to determine if it would be able to support life. That would include analyzing the moisture content, as well as the pH of the soil, as well as look for potential organic matter that already exists. So in order to collect the soil sample that we need, the rover will be equipped with a mechanical system including an auger that will be pushed down into the soil in order to scoop it up. Our soil sample will be like a core sample, in that with a window in the auger, we will be able to look at various depths in the sample that we took, using our set of near-infrared lasers. In addition to our lasers, we'll also have a set of standard probes, one for moisture and one for pH, and hopefully this will add a bit of redundancy to our data.
For the equipment servicing task, the arm plays a major role. The arm is very dexterous and has a wide range of motion. This allows it to easily flip switches, turn valves, and push buttons, which might be expected during the equipment servicing task. The end effector can also rotate continuously, allowing it to rotate valves without being restricted by wires.
For the terrain traversing task, we have completely redesigned the rocker bogie suspension to make use of in-wheel motors to give us the most ground clearance from rocks as possible, as well as stiffer suspension and a precision gearbox to get the most response out of the rocker bogie. At the same time, we wrote software for custom motor controllers, allowing us to intelligently respond to things such as getting caught up on rocks or steep slopes.
So to wrap things up, we worked really hard this year to have a good design, and we think that we're going to have an excellent rover come May 28th when we come down there and compete. Thank you for watching our video. This is Thomas Johnson, the Space Design Team. See you down there.